Now that we've talked a little bit about Riemann sums, let's talk about their main purpose, which is to actually find the area underneath a curve. If I consider some kind of graph, and I have this point A and B, if I were to break this up into little rectangles and find each of their area and then add them up, that would be a Riemann sum. So the idea with this is, as I'm taking these Riemann sums, the smaller and smaller I make these rectangles, the closer and closer of an approximation I'm going to have. So what I really want is going to be to take the limit of these sums as n goes to infinity, as I get infinitely many rectangles. So let's do an example. Let's suppose I want to find the area under the curve of f of x equal to x squared between 0 and 1. Well, first we need to start setting this up. We're going to take the sum, and I'm not going to put a number on the top. I'm just going to put n, and k equal to 1. I need to know if I'm doing left, right, or midpoint, and ultimately it doesn't matter, so I'm going to do right endpoints because they're a little bit easier. So in that case, I need to substitute in delta x times k. So I have k delta x squared, and then I need to multiply the whole thing by delta x. Well, simplifying this gives me k times delta x cubed. The formula for a k value, or k squared delta x, for k squared was n plus 1, 2n plus 1 over 6. And it's important to now realize exactly what this delta x is. So delta x is actually the length of my interval, 1, divided by the number of subintervals, which is n. And I need to cube this. Times n plus 1, 2n plus 1 over 6. And now I'm going to have to take the limit as n goes to infinity. On the top of this thing, if I multiply it out, I'm going to have 2n cubed plus some other stuff. And on the denominator, I'm going to have 6n cubed. And it's important that I realize this because if I take the limit as n goes to infinity, since the degree on the top is the same as the degree on the bottom, I can just look at coefficients, 2 over 6. So my area underneath this curve is going to be 1/3. Let's look at another example. So we can just take the limit of this sum as we go out to infinity and we'll get the results that we need. But there is some shorthand notation. A lot of times we'll write this using this term. This is my integral sign. It looks like a stretched out S. This a and b are my limits of integration. It tells me the bounds. This is called an integrand. And the dx part is called the differential. And in the next couple of videos, we're going to show how to use this a little bit easier. We're going to talk a little bit more about this notation and how to easier evaluate these sums without actually having to add up all of these terms.